Hello and welcome. Today we shall tell you about developing photographs. The subject expert for today is Mr. Kumar Barun, a professional photographer working as senior photographer with fabfashion.com. And I am Sakshi Mandwal. Developing photographs. Introduction. Photographs are precious since they are significant memories which are cherished and preserved. But in order to keep these memories physically alive, we need to process the film. Developing photographs is a very technical process. In today's module, we would understand A. What are the various processes involved in creating a physical picture? B. Which chemicals are used and how to prepare photographs? C. How to develop black and white films. D. The process of developing colored film. E. The process of photograph processing. F. The final print. Photographic process. The production of film density and the formation of a visible image is a two-step process. The first step in this photographic process is the exposure of the film to light, which forms an invisible latent image. The second step is the chemical process that converts the latent image into a visible image with a range of densities or shades of grey. Film density is produced by converting silver ions into metallic silver, which causes each processed grain to become black. Each film grain contains a large number of both silver and bromide ions. The silver ions have a 1 electron deficit, which gives them a positive charge. On the other hand, the bromide ions have a negative charge because they contain an extra electron. Each grain has a structural defect known as a sensitive speck. A film grain in this condition is relatively transparent. The development. The invisible latent image is converted into a visible image by the chemical process of development. The developer solution supplies electrons that migrate into sensitized grains and convert the other silver ions into black metallic silver. This causes the grains to become visible black specks in the emulsion. Radiographic film is generally developed in an automatic processor. The 4 components correspond to the 4 steps in film processing. In a conventional processor, the film is in the developer for 20 to 25 seconds. All 4 steps require a total of 90 seconds. A film processor developing. When a film is inserted into a processor, it is transported by means of a roller system through the chemical developer. Although there are some differences in the chemistry of developer solutions supplied by various manufacturers, most contain the same basic chemicals. Each chemical has a specific function in the development process. Reducer. Chemical reduction of the exposed silver bromide grains is the process that converts them into visible metallic silver. This action is typically provided by 2 chemicals in the solution, phenidone and hydroquinone. Phenidone is the more active and primarily produces the mid to lower portion of the grayscale. Hydroquinone produces the very dense or dark areas in an image. Activator. The primary function of the activator, typically sodium carbonate, is to soften and swell the emulsion so that the reducers can reach the exposed grains. Restrainer. Potassium bromide is generally used as a restrainer. Its function is to moderate the rate of development. Preservative. Sodium sulfide, a typical preservative, helps protect the reducing agents from oxidation because of their contact with air. It also reacts with oxidation products to reduce their activity. Hardener. Glutaraldehyde is used as a hardener to retard the swelling of the emulsion. This is necessary in automatic processes in which the film is transported by a system of rollers. Fixing. After leaving the developer, the film is transported into a second tank, which contains the fixer solution. The fixer is a mixture of several chemicals that performs the following functions. Neutralizer. When a film is removed from the developer solution, the development continues because of the solution soaked up by the emulsion. It is necessary to stop this action to prevent overdevelopment and fogging of the film. Acetic acid is in the fixer solution for this purpose. Clearing. The fixer solution also clears the undeveloped silver halide grains from the film. Ammonium or sodium thiosulfate is used for this purpose. The unexposed grains leave the film and dissolve in the fixer solution. The silver that accumulates in the fixer during the clearing activity can be recovered. The usual method is to electroplate it onto a metallic surface within the silver recovery unit. Preservative. Sodium sulfite is used in the fixer as a preservative. Hardener. Aluminium chloride is typically used as a hardener. Its primary function is to shrink and harden the emulsion. Wash. Film is next passed through a water bath to wash the fixer solution out of the emulsion. It is especially important to remove the thiosulfate. If thiosulfate, hypo, is retained in the emulsion, it will eventually react with the silver nitrate and air to form silver sulfate, a yellowish brown stain. The amount of thiosulfate retained in the emulsion determines the useful lifetime of a processed film. After the completion of the process, we have a negative image of the original scene. It is a negative in the sense that it is darkest, has the highest density of opaque silver atoms in the area that received the highest light exposure. In places that receive no light, the negative has no silver atoms and is clear. In order to make it a positive image that looks normal to the human eye, it must be printed onto another light-sensitive material, usually photographic paper. Dry. The final step in processing is to dry the film by passing it through a chamber in which hot air is circulating. Developing color film. Now we proceed to learn the process of developing color film. If your film were a color negative type that gives you a print when returned from the photoprocessor, the processing chemistry is different in several major ways. The development step uses reducing chemicals and the exposed silver halide grains develop to pure silver. Oxidized developer is produced in this reaction, and the oxidized developer reacts with chemicals called couplers in each of the image forming layers. This reaction causes the couplers to form a color, and this color varies depending on how the silver halide grains were spectrally sensitized. A different color forming coupler is used in the red, green and blue sensitive layers. The latent image in different layer forms a different colored dye when the film is developed. Red sensitive layers form a cyan colored dye. Green sensitive layers form a magenta colored dye. blue sensitive layers form a yellow colored dye. The resultant color negatives look very bizarre. First, unlike your black and white negative, it contains no silver. In addition to being a color opposite, negative, the negatives have a strange orange-yellow hue. They are a color negative in the sense that the more red exposure, the more cyan dye is formed. Cyan is a mix of blue and green, or white minus red. The overall orange hue is the result of masking dyes that help to correct imperfections in the overall color reproduction process. The green sensitive image layers contain magenta dye, and the blue sensitive image layers contain yellow dye. The colors formed in the color negative film are based on the subtractive color formation system. The subtractive system uses one color, cyan, magenta or yellow, to control each primary color. The additive color system uses a combination of red, green and blue to produce a color. Your television is an additive system. It uses small dots of red, green and blue phosphor to reproduce a color. In a photograph, the colors are layered on top of each other. So a subtractive color reproduction system is required. Red is controlled by cyan dye, green is controlled by magenta dye, blue is controlled by yellow dye. Color negatives are not very satisfying to look at. They are small and the colors are strange, to say the least. In order to make a color print, the negatives must be used to expose the color print paper. Certain factors related to processing have to be kept in mind during the development of film, which are given herewith. Processing. The effective sensitivity of film depends on several factors associated with the development. The type of developer, developer concentration, developer replenishment rates, developer contamination, development time, development temperature. In most medical imaging applications, the objective is not to use these factors to chance or vary film sensitivity, but rather to control them to maintain constant and predictable film sensitivity. Developer composition. The processing chemistry supplied by different manufacturers is not the same. It is usually possible to process a film in a variety of developer solutions, but they will not all produce the same film sensitivity. The variation in sensitivity is usually relatively small, but must be considered when changing from one brand of developer to another. Developer concentration. Developer chemistry is usually supplied to a clinical facility in the form of a concentrate that must be diluted with water before it is pumped into the processor. Mixing errors that result in an incorrect concentration can produce undesirable changes in film sensitivity. Developer replenishment. The film development process consumes some of the developer solution and causes the solution to become less active. Unless the solution is replaced, film sensitivity will gradually decrease. In radiographic film processes, the replenishment of a developer solution is automatic. When a sheet of film enters the processor, it activates a switch that causes fresh solution to be pumped into the development tank. The replenishment rate can be monitored by means of flow meters mounted in the processor. The appropriate replenishment rate depends on the size of the films being processed. Developer contamination. If the developer solution becomes contaminated with another chemical, such as the fixer solution, abrupt changes in film sensitivity can occur in the form of either an increase or decrease in sensitivity, depending on the type and amount of contamination. Developer contamination is most likely to occur when the film transport rollers are removed or replaced. Development time. When an exposed film enters the developer solution, development is not instantaneous. It is a gradual process during which more and more film grains are developed, resulting in increased film density. The development process is terminated by removing the film from the developer and placing it in the fixer. To some extent, increasing development time increases film sensitivity, since less exposure is required to produce a specific film density. In most radiographic film processors, the development time is usually fixed and is approximately 20 to 25 seconds. However, there are two exceptions. So-called rapid access film is designed to be processed faster in special processors. Some, but not all, mammographic films will produce a higher contrast when developed for a longer time in an extended cycle processor. Development temperature. The activity of the developer changes with temperature. An increase in temperature speeds up the development process and increases film sensitivity because less exposure is required to produce a specific film density. The temperature of the developer is thermostatically controlled in an automatic processor. It is usually set within the range of 90 to 95 degrees Fahrenheit. Light color, wavelength. Film is not equally sensitive to all wavelengths, colors of light. The spectral sensitivity is a characteristic of film that must be taken into account in selecting film for use with specific intensifying screens and cameras. In general, the film should be most sensitive to the color of the light that is emitted by the intensifying screens, intensifier tubes, cathode ray tubes, CRTs, or lasers. Blue sensitivity. A basic silver bromide emulsion has its maximum sensitivity in the ultraviolet and blue regions of the light spectrum. For many years, most intensifying screens contained calcium tungstate, which emits a blue light and is a good match for blue sensitive film. Although calcium tungstate is no longer widely used as a screen material, several contemporary screen materials emit blue light. Green sensitivity. Several image light sources including image intensifier tubes, CRTs and some intensifying screens emit most of their light in the green portion of the spectrum. Film used with these devices must, therefore, be sensitive to green light. Silver bromide can be made sensitive to green light by adding sensitizing dyes to the emulsion. Users must be careful not to use the wrong type of film with intensifying screens. If a blue sensitive film is used with a green emitting intensifying screen, the combination will have a drastically reduced sensitivity. Red sensitivity. Many lasers produce red light. Devices that transfer images to film by means of a laser beam must therefore be supplied with a film that is sensitive to red light. Safe lighting. Dark rooms in which film is loaded into cassettes and transferred to processors are usually illuminated with a safe light. A safe light emits a color of light the eye can see, but that will not expose the film. Although film has a relatively low sensitivity to the light emitted by safe lights, film fog can be produced with safe light illumination under certain conditions. The safe light should provide sufficient illumination for darkroom operations but not produce significant exposure to the film being handled. This can usually be accomplished if certain factors are controlled. These include safe light colors, brightness, location, and duration of film exposure. The color of the safe light is controlled by the filter. The filter must be selected in relationship to the spectral sensitivity of the film being used. An amber-brown safe light provides a relatively high level of working illumination and adequate protection for blue sensitive film. Type 6B filters are used for this application. However, this type of safe light produces some light that falls within the sensitive range of green sensitive film. A red safe light is required when working with green sensitive films. Type GBX filters are used for this purpose. Selecting the appropriate safe light filter does not absolutely protect film because film has some sensitivity to the light emitted by most safe lights. Therefore, the brightness of the safe light, bulb size and the distance between the light and film work surfaces must be selected so as to minimize film exposure. Since exposure is an accumulative effect, handling the film as short a time as possible minimizes exposure. The potential for safe light exposure can be evaluated in a dark room by placing a piece of film on the work surface, covering most of its area with an opaque object, and then moving the object in successive steps to expose more of the film surface. The time intervals should be selected to produce exposures ranging from a few seconds to several minutes. After the film is processed, the effect of the safe light exposure can be observed. Film is most sensitive to safe light fogging after the latent image is produced but before it is processed. Processing quality control. There are many variables such as temperature and chemical activity that can affect the level of processing that a film receives. Each type of film is designed and manufactured to have specified sensitivity, speed, and contrast characteristics. Overprocessing. Overprocessing can increase sensitivity. The contrast of some films might increase with overprocessing up to a point and then decrease. A major problem with overprocessing is that it increases fog, base plus fog density, which contributes to a decrease in contrast. Artifacts. A variety of artifacts can be produced during the storage, handling and processing of film. Bending unprocessed film can produce artifacts or kink marks, which can appear as either dark or light areas in the processed image. Artifacts can be produced during processing by factors such as uneven roller pressure or the accumulation of a substance on the rollers. This type of artifact is often repeated at intervals corresponding to the circumference of the roller. Making the prints black and white. After the completion of development process, we get a black and white negative and make a print of the same. The user has the choice of an enlargement or a direct contact print. If the users want a large size print than the original negative, he will need an enlarger, which is basically a projector with a lens for focusing the image and a controlled light source. The negative is placed in the enlarger and it is projected onto a flat surface that holds the paper. The image is carefully examined to ensure that it is in focus. If not, adjustment can be made to the lens and projection length. Once the size of the image and its focus are satisfactory, all the lights are shut off and the black and white paper is placed onto the flat surface. The paper is exposed for a specified amount of time using the light from the enlarger. A latent image is formed in the exposed silver grains. This time, the densest areas of the negative receive the least amount of light and therefore become the brightest and most reflective parts of the print. The development process is much the same as for the black and white negative film, except the paper is much larger than the film and agitation of the processing chemicals becomes more critical and more difficult. The final image is actually developed silver, and by carefully washing the prints to remove all the unwanted materials, these prints can last a very long time. Making color prints. Prints from color negatives are usually done by a large central lab that handles printing and processing for many local drug stores and supermarkets, or they may be done in-house using a mini lab. The mini lab is set up to do one roll of film at a time, whereas the product houses splice many rolls together and handle a high volume of pictures on a semi-continuous basis. In either case, the steps are the same as already discussed for generating a black and white negative image. The major difference comes in the printing process, where long rolls of color paper are preloaded into a printer. The color balance is adjusted by adding subtractive color filters to make the print more pleasing, particularly when it has been exposed incorrectly. There is only so much correction that can be done. So don't expect miracles. Once a full roll of paper is exposed or a single roll of film has been printed, in the case of a mini lab, the paper is processed. Here are the steps in developing the color print paper after it is exposed. The latent image sites are developed and oxidized developer molecules combine with the color-forming couplers to create a silver image and a dye image. The reaction is stopped by a washing step. The silver image and any remaining unexposed silver halide is removed in a combined bleach plus fix solution called the Blix. The print is then carefully washed to remove any residual chemicals. The print is dried. Once again, the gelatin binder swells to allow the processing chemicals access to the silver halide grains and allows fresh water to rinse out the byproducts. The colored image should contain no residual silver. As a final example of color printing process, let's take a look at a negative that was exposed to a pure yellow object. When the resultant negative is placed in the printer and white light is shown through the negative onto the color paper, here is what happens. The white light exposure is the equivalent of a color printer exposure. Only blue light gets through the color negative and exposes the color paper. The exposed color paper then forms yellow dye in the blue sensitive layer and the original color is reproduced. And now it is time for a quick recap. Development of a photograph in both color and black and white is a three-tier process which involves developing of the film, processing of the film, and the final printing or making of the film into a photograph. This process is technically fashioned and once understood can help in creating wonderful photographs. That is all that we had for you in this episode. Thank you so much for watching. Till the next time, it's a goodbye.